Talk is by Kasia Rejzner. Thank you very much.
Okay, thank you so much for the invitation to this nice conference. Oh dear. Yes, so, thank you very much for the invitation. I'm going to continue on the topic already started in the talk of Stefan. So, he mentioned BV, BRST method. Well, I will, to a large extent, continue on that. Okay, so first of all, I want to tell you about the general framework in which I'm working, which is slightly different from what was in the other talk, so I think it's worth going over it a bit. And then I will explain the algebraic side of what Stefan started, and finally, talk about some examples. Okay, so the general, in broad terms, the framework I'm working in is algebraic quantum field theory, and this is, as you know, not very new. It goes back to Haag and Kastler, so there was a seminal work of Haag from '59, and then the paper with Kastler in '64. So it's not a new framework, but it has many features that keep coming back and get new realizations in different contexts. So my talk is going to be about a slightly new realization of that idea. But let me first tell you what's the idea. So one thinks about a quantum field theory model in terms of algebras you assign to regions of spacetime. So we start with Minkowski spacetime. Most talks were on flat spacetime here. I'm working in Lorentzian signature, so Minkowski spacetime. I'm not specifying a dimension at the moment, but probably most of you want to think 4, because this is the physical dimension. And to each bounded region in spacetime, I assign the algebra of observables that can be measured in that region. So this is a mathematical structure. Physical interpretation is, well, essentially all the quantum observables that you can measure in some bounded region, like for example this room, over a finite time. So for example, over the duration of this lecture. Okay, so if I go to a larger region, for example, all the observables in Cambridge you can measure during the duration of this program. This is much more observables, I expect. So the algebra of the smaller region, so of this room during my talk, should be included in the larger one. And this is the very basic physical assumption. Now, this assignment of algebras to regions builds a net, so we obtain a net of algebras. And I want to impose further properties on that net, which are, again, physically motivated. So here I want to mention the causality and the time slice axiom. So the causality means that things which are space-like separated should be, in some sense, independent. So here, if I have two regions, O1 and O2, which are space-like to each other, so maybe let me draw a quick picture. So this is 2 dimensions, this is space, this is time. This structure here is the light cone. This is future. So this is the region inside. This is past. And everything outside the light cone is space-like. Okay, so commutativity for space-like regions. This is the notion of causality. And then there is a time slice axiom, which tells me that the system has something. So this is a quantum version of having well-posed initial value problem. So if I have n, which is a neighborhood of a Cauchy surface over a region O, so again, let me draw it. So if I have region O, a Cauchy surface, and I have a neighborhood of that, ouch, then I want the algebras to be isomorphic. So all the information I need about the observables of a region can be really just obtained from that time slice. Okay, so now these are the axioms. These are not all the axioms of Haag-Kastler, but let's say I want to focus on those. And I'm interested in constructing models that satisfy these axioms. Okay, so now what are the generalizations of this? Well, first of all, I can replace M with some more general Lorentzian manifold, and I want to focus on those which are globally hyperbolic. So being globally hyperbolic means that it has a Cauchy surface. So like that guy on the board, Cauchy surface is a good hypersurface for initial data. So that's why it's relevant. Right, so this generalization goes under the name of locally covariant QFT, and here I want to mention some people who contributed. So there is a paper of Brunetti, Fredenhagen, Fesch, and Hollands and Wald. So these were the basic foundations of that. And there is also an interesting paper of Fesch, which came a bit later, which also studies the problem of QFT in this locally covariant framework, trying to understand what does it mean to have same physics on different spacetimes. Okay, so now why is the algebraic approach so good for curved spacetime? I want to argue. Well, it allows to separate the dynamics from the specification of the state. So you have seen that up to now I only talked about the algebras, so you can construct your net of algebras, and then after this is done, then you can think about representation. So in particular on Minkowski, you want to think about the vacuum representation. Well, on a generic curved spacetime, there is no preferred vacuum. So it's good that these two things are somehow separated. So you think of a class of states instead. Okay. Moreover, so this is one direction to generalize. The other direction is to go into perturbation theory. So you allow these algebras assigned to regions to be formal power series in H bar. And this is probably outrageous here because, okay, I think all the results, most of the results up to now were non-perturbative. However, if you want to be able to talk about Young-Mies in 4 dimensions, the way Stefan was talking, you might want to live with perturbation theory. So we slightly weaker the axioms, but then we allow for a class of physically interesting models which are relevant in particle physics. Okay, whoops. So this framework where, you know, we allow for a bit of perturbative methods is called perturbative AQFT. So P is small because we are still a bit embarrassed that it's there, and we hope to get rid of it. Yes, please.
So how much of the theory of von Neumann algebras carries over to the algebras in the...
Well, if it's perturbative, then you don't actually work with von Neumann algebras, you work with topological star algebras instead. However, if you can show some non-perturbative results, then you're probably back in the von Neumann business. So, yeah, I mean, okay. There's a convergence problem.
You have a double commutant theorem, for instance, for this star?
No, that wouldn't work. I mean, you can, but that wouldn't have a nice properties. But okay, I mean, there are some results which are where you can show convergence and you get actual net of von Neumann algebras. So, but that's a different talk. That's the talk I already gave here, I think a year ago. So, okay. So what are the basic methods and results? So let me now give you an overview of what has been done, and this is by topic, not really by chronology. So first of all, okay, so in order to construct the model, we start with a free theory, which we obtained by sort of deformation quantization from the classical theory. And here, the basic idea is to, well, define this classical theory using the method of Pius, which allows you to construct a canonical bracket in a very nice covariant way. And here I want to mention Dutch, Fredenhagen, and Brunetti in various combinations. So these were works from 2000s when this was worked out. Now the interaction is introduced in the Epstein-Glaser framework, so we need to do some renormalization. And to do renormalization in position space, it's convenient to work in the Epstein-Glaser. This is, you might recognize, it's again an old result from the 70s, but works very well on curved spacetime. But this came much later. So, all right, and now there is also the gauge theories, where some homological algebra is used, and there is the work of Stefan from 2007, and there is my work with Fredenhagen from 2011, which goes a bit more into the abstract structure. So I will talk about it most of this talk. Right, so you can also go further. I mean, Yang-Mills theory is an example of gauge theory. You can also treat effective quantum gravity using these methods, and there is a paper of Brunetti, Fredenhagen, and myself, 2013, and there is a paper on construction of gauge invariance observables by Markus Wöhl, which is a recent one. And finally, okay, so in this Epstein-Glaser approach, you introduce a cutoff, a diabatic cutoff to the interaction to somehow avoid infrared infinite volume problem. Then you have to take the adiabatic limit, and the existence of this weak adiabatic limit in Epstein-Glaser was shown by Pavel Duch in 2018. So I mean, it was also to some extent shown by Epstein-Glaser earlier, but there were some gaps in that proof. And also you can treat thermal states. So there is a nice paper of Fredenhagen-Lindner from 2014, and again a generalization by Drago, Haag, and Pinamonti from 2016, where they also treat some more general problem. Okay, so that's more or less, that's not a complete list of what's going on in the field, but just some highlights. Right, so why use this whole business for gauge theories? Well, okay, so that can be related to the question, why use the V formalism at all? And again, BV formalism was not invented by anyone in this room. It was invented by Bartel and Wilkowinski. It was only put in a slightly more mathematical framework recently. But it does work for quantization of gauge theory. And in fact, in this version we developed, it allows to treat a very general class of models, which includes effective quantum gravity. So that was my initial motivation to actually start working on that. And also, and this is related to that, it allows, at least in principle, to quantize observables which are non-local. Then there are some technical problems, but at least there is a way to pose the problem, and in some cases there is a way to solve it. And again, this is important for quantum gravity. Also, it's a very nice geometrical way of thinking, so that I hope I will be able to tell you later. And okay, well, in a sense, there is a framework, so there is a machinery which you insert the model and it gives you an answer, which is again useful because you don't have to worry whether this works or doesn't work. There are some general abstract results which tell you that if you insert a theory, turn the crank, then the results will come out correctly. So what you're computing is the thing you want to compute. All right, and what I'm going to focus on here, well, it allows to define the BRST differential abstractly, so on the algebraic level, which in this way of thinking in terms of algebras separated from states is advantageous, because we know about this operator in the abstract, we don't necessarily have to go to the concrete representation and define it via a chart. So we can do it. However, this is not necessarily, at least for the definition. For this talk, I will use two works with Fredenhagen on Bakarin-Wilkowinski in classical and quantum field theory in this perturbative AQFT approach. So these are again a bit old, but I think it makes sense to really keep it basic. Okay, so let's start constructing the model. The first bit of physical input is the spacetime on which we want to construct things. And then we have to specify the configuration space, so choice of objects we want to study. And these could be scalars, vectors, tensors, or whatever fields we want. And typically, it's going to be a space of smooth sections of some vector bundle. For the scalar field, which is the simplest example, it's just smooth functions on the manifold. And for Yang-Mills theory, which will be the leading example in this talk, this is one forms valued in a Lie algebra K of a compact Lie group. And one can also do effective quantum gravity, so gravity quantized perturbatively as an effective theory. And here the configuration space is metric perturbation. So this is covariant to tensors. And because I want to avoid overwhelming you with the notation, I will always denote the element of the configuration space by phi if I talk about it in general terms and not specify the theory, but you can then insert any of those into that slot. So there are things which will work in very general situation. Okay, so for the dynamics, I will use a certain modification of the Lagrangian formalism. So covariant, because we worked on a very general curved spacetime. Okay, so first of all, classical observables. These are smooth functions on the space of configuration. So an observable takes a field configuration and returns a number. And okay, smoothness, we can think of it as a sort of regularity condition. So the first one we impose. I will drop this M for the rest of the talk because we might think of fixed spacetime. So there is no need to have it in all the formulae. So I will just write E for the configuration space and C infinity of EC for the observables. Okay, I need some notion of localization because I want to assign observables to regions. So I want to know where they are localized. And here there is a definition of the spacetime support, which is of importance. So a support of F is defined as the space of points such that if I perturb the field by a perturbation psi, which is supported in the neighborhood of this point, then the functional sees the difference. So these are observables that are sensitive to perturbations in that given neighborhood. So it's to a large extent a straightforward generalization of the distributional support. If this was a linear functional, then this would be just the definition of a support as a distribution. So not too strange. Again, there is a special class of functionals, namely the local ones. So you can express them as integrating some function on the jet bundle. So a jet is just the value of the field and its derivative. And here I want to think at least locally of a finite jet. So a local functional would be given for each phi as integrating some function of the finite jet at the point. Because I want an algebra, I will consider products of such things. So these are the most nice functionals. Things like phi squared, phi to the fourth, everything would fit into that category. So these are local interactions. Right, and there is maybe a bit more exotic class of observables which are considered as auxiliary objects. So you can think of them as regularized UV, regularized interactions. So a functional is regular if all its derivatives are smooth. So for local functional like phi to the fourth, the derivatives would involve some multiples of delta distributions and its derivatives. But okay, if you want something more regular, you can restrict yourself to functionals which are obtained just by integrating fields with smooth, compactly supported functions. These are not entirely physical, but you can think of them as auxiliary to just understand the algebraic structure. Okay, so that was the kinematics. Now let me say something about dynamics. So I want to introduce a Lagrangian. So here the Lagrangian would be depending on a cutoff, as I said at the very beginning in the introduction. In the Epstein-Glaser method, first of all, you have a Lagrangian, you have interaction with a cutoff, and then you remove this cutoff at the later stage using the adiabatic limit. So a Lagrangian, already in the classical theory, I can set it up this way. It's a map from a space of test functions, so this will be the cutoff functions to local functionals. And let me just give you a few examples. So here there's the free scalar field. This cutoff is just multiplying the usual Lagrangian density. It's exactly the same situation with the Young-Mills. This is the known Young-Mills Lagrangian. And here is the Lagrangian, the Einstein-Hilbert Lagrangian for gravity. Okay, so that now would be completely useless if we were not able to remove this cutoff. So in classical theory, this is very, very simple. So I take the variation of my Lagrangian, of my action, and in the direction given by some compactly supported perturbation. And I choose my cutoff function to be 1 on the support of that perturbation. So here there is psi, and here I choose a cutoff such that it's equal 1 around the support of psi. And this definition, because of locality, this definition does not depend on this f anymore. So this actually defines me the Euler-Lagrange derivative, which I want to understand as a one form on the configuration space. So that you have to think maybe slightly more abstract. So the configuration space is where your fields live. The action is more or less a function on that, and then the derivative, Euler-Lagrange derivative, is one form on the configuration space. And now the equations of motion are the condition that this one form vanishes on a given field. So in geometrical terms, the space of solutions to classical equations is the zero locus of this one form obtained from variation of the action. So this one form is going to be important, this ds. So part of this analysis in BV is to characterize this critical locus in a convenient way. Okay, so that was the field equations. Now the symmetries, and again there is a geometrical interpretation for what symmetries are. These are identified with vector fields on the configuration space. So here there is a two-dimensional representation of an infinite dimensional manifold. So here is the configuration space. Here is some configuration phi living in it. And you can think of flow lines, directions in that configuration space given by vector fields. And I will impose some regularity condition on those, so I want them to be in some sense local, the way that observables were local. And okay, there are some more functional analytic requirements, which however I won't mention here because that would make the talk twice as long. Okay, but let's call by V the space of sufficiently nice vector fields so that this analysis makes sense. And they act on the space of functionals. Again, F is my notation for sufficiently nice functionals. They act as derivations. So I take the variation of the functional and then I contract it with that vector field. And then I'm using a notation which is suggestive of this geometrical interpretation. So what's a symmetry? So a symmetry of the action, this you know from classical mechanics, should correspond to some direction in the configuration space where the action is constant, so that the derivative would vanish. So let's try to make sense of it using the objects we have. So we have this one form ds, which gives equations of motion. So x is a symmetry if, after contracting with this vector field, if I contract it with this one form, then I get identically 0. Okay, so I have two ingredients. I have equations of motion and symmetries, and now I want to combine those in some sort of algebraic framework that will tell me, first on the classical levels, which observables are invariant under these symmetries and which observables can be thought of as functionals on the space of solutions. So this is going to be the next step. Now, what, again, Stefan already said about the general idea, but maybe let me reiterate this because this gets very technical, so it's good to have an overview of the ideas. So what is the problem classically? So classically, if we have local gauge symmetries, then the Cauchy problem is not well posed, and we run into all sorts of troubles with redundancy in the space of solutions. So you might be tempted to get rid of that redundancy just by forming some sort of quotient. So that's one way of dealing with it. However, I mean, when you form a quotient, then you end up with a space of fields. You end up with a configuration space which is much more complicated and geometrically maybe possibly very ugly and hard to quantize. So sometimes it's easy in some models, you can actually do it directly, but in general, especially if you have these symmetries that don't close off shell, then this is terrible. So instead of forming this quotient, I extend the space of configurations to something larger. I formulate my field equations on that something larger, and that something larger also has a structure which tells me where the redundancy is. So that's more or less the idea. And yeah, I mean, quotients are hard, so I want to really remain on the level of vector spaces and linear maps between vector spaces. And this is what homological algebra is about. So take your problem and express everything in terms of linear algebra. Okay. Okay, so VV, Batalin-Wilkowinski, maybe they didn't formulate it exactly in this way, but okay, somehow this idea was there already. This BV construction allows to perform that program, so allows to extend your theory in a controlled way, keep track of the redundancies, and then come back to the physical information at the end. And more importantly, you can do it on the level of classical theory, and then there is a control way to quantize it and then recover physical information after the quantization has been done. Okay, and one of the ways to keep track of things is use of the grading. So we will be working with graded algebras. So up to now, they were just algebras, and now there is this extra structure of the grading. And this is somehow where things like ghosts would come in. So this would be graded field configurations. So let's start with the this quotient by the equations of motion. So I want to just forget about symmetries for a moment. I want to characterize the space of functionals on solutions. So I have my form ds, and I define a map on vector fields from vector fields to functionals as contraction with that one form, and I denote it by delta S. So let now ES be the space of solutions, so the zero locus to that one form, and I want to characterize the functionals on this. So first of all, okay, let's look at the functionals which vanish on the solution space. So this is the redundancy in my description, and I assume that they are all in the image of delta S. And looking at that, well, it's clear that this is indeed vanishing on the space of solutions, because ds by definition vanishes on the space of solutions. So far, so good. So the space of relevant things, so the space of functionals that you can think of those on the space of solutions, is the quotient of all the functionals on the whole configuration space modulo those that vanish on solutions, so modulo that redundancy. Instead of forming that quotient, I will now resolve this using the construction called Koszul complex, and this delta S is in fact what's known in mathematics as Koszul differential. And you can see also, based on the analysis before, that symmetries constitute the kernel of that differential, since if X is a symmetry, then this object here, delta S on X, is identically 0. So here is a baby version of the differential complex I want to work with. So here in grade 0, I keep all my observables, classical observables. In grade 1, I keep my vector fields. And in grade 2, I keep the symmetries. And the idea, okay, so here I contract a vector field with ds, so this is this map. From F to here is just 0, and symmetries are just included as a subset of all the vector fields. So, okay, let's now do some homological algebra. Stefan already mentioned that homology means that you take the kernel of this little differential by the image in each step, in each grade. So let's look at the zero homology of this complex. We have the kernel of this map, which is all of F, because this is just a zero map, by the image of delta S, which by definition is things that vanish on the space of solutions. So H0 of this complex give me exactly the quotient I wanted. So it's a prototype of the construction which I will now start building from this baby example. So we have H0, okay, we can now try to expand this complex into some sort of graded algebra. And let's start with the situation where there are no non-trivial symmetries. So there are no symmetries that do not vanish identically on the space of solutions. And in that situation, I'm actually almost there with my resolution. So I build the following object. So I take the exterior algebra of V. So these are anti-symmetrized tensor products of V with itself, and a differential which is defined, as I said, on V, and then extended to this big exterior algebra by the graded Leibniz rule. So it's enough to know it in degree 1, and then in higher degrees you just extend it by demanding the Leibniz rule. This guy is then called the Koszul complex, actually Koszul-Tate, but that would be a bit trivial example. The case with no non-trivial gauge symmetries is actually the case of the massive real scalar field. So for that, there is already some non-trivial information in the BV complex, but there are no gauge symmetries yet. So the BV complex contains only the information about the equations of motion, in the sense that the space of functionals on the solution space is given as H0 of this. And the bonus here is that you can do it as an exercise. Higher homologies vanish. So if there are no symmetries, and then you just extend everything by the graded Leibniz rule, then you find out that in this complex, all but the zero homology vanish. Such a structure is called resolution. So everything but zero homology vanishes. Yes, please.
So since V is infinite dimensional in general, so this complex is infinite, but when you take the homology, does it stop after a while? Or
Yeah. I mean, it stops very quickly because only H0 is non-trivial and the higher homologies are zero, so are empty. So all the homology is concentrated in degree 0.
No, I'm saying in general, not in
In general. In general, yes. So, but this is non-trivial. So if you have symmetries, then you have to prove something. But there is a result in homological perturbation theory saying that, okay, I don't remember exactly assumptions, but in physically relevant examples, in the sense of formal power series, so you can, this procedure, which I only started the first step of, will terminate after finitely many steps. So it's not too bad, but one has to be careful the way you phrase it, because there is some perturbation parameters and some grading, but it's set up in such a way that actually terminates. Okay, so that was the situation with no symmetry, so relatively boring, but good as a warm-up. Let me maybe, before I go to something more complicated, let me run a few remarks about the notation. So, and this is maybe a bit, formal. It's a very suggestive notation. You can think of an infinite dimensional vector field as something, as a derivation on functionals. So you take a derivative of a functional and contract with the value of the vector field at a point. And in analogy to a finite dimensional situation, you can represent those in terms of some integral kernels. So this is then the action on a given functional. And these derivatives here, you can think of them as formal generators of V, of the space of vector fields. And these are called, in this language, anti-fields. So one uses various notations for this, but the one I like is the one with the sort of double dagger. So if you think of them as generators of V, then you can write all the elements in the Koszul complex in terms of these generators. So everything can be done on the level of integral kernels in the end. Which is, so if you're working with local quantities, this is very good, because the problem of actually computing these cohomologies is reduced to a problem where, at least locally, you have finite dimensional spaces. Okay, so there is also another nice bit of structure. These are vector fields. The exterior algebra over that is multi-vector fields. And there is a nice graded bracket called the Schouten bracket on that. Again, this is a geometrical structure. Schouten bracket was not invented for the purpose of quantizing gauge theories. It's a known structure in geometry. But in this context, it goes under the name of anti-bracket. So anti-fields and anti-bracket. But again, these are things which geometrically have independent life of their own. So this derivation is almost inner derivation with respect to that bracket. One only has to adjust the cutoff function in the interaction to be 1 on the support of the given vector field. But modulo that, you can write ds on x as a bracket with the action. Okay, now let me go to symmetries. So if we have a theory like Young-Mills or gravity, then we will have a non-trivial space of symmetries. And in the simplest case, I can characterize this as in terms of some Lie algebra S tensored with coefficients that can be arbitrary functions. In general, this is always some Lie subalgebra of V, but the difficulty somehow is to be able to represent it as something of this form. This doesn't always work. Sometimes you have to do something more general, so Lie algebroid or whatever other structure. But anyway, so let's focus on this situation, because this is good for Young-Mills theories, where the space of symmetries is Lie algebra valued functions, and in gravity these are vector fields on your manifold. So what we want to construct in the end is the space of on-shell functionals. So this we already know from the previous slides, which are on top of that gauge invariant. So invariant under the action of that Lie algebra. Invariants and Lie algebras, you can take your favorite homological algebra textbook, for example, Weibel, and find out that there is a nice tool for this called Chevalier-Eilenberg complex. So here there is a similar trick to what we did before. So you take exterior algebra of the dual of that Lie algebra with coefficients in functionals, and a differential which in degree 0 acts essentially as taking this Lie algebra action, taking a vector field corresponding to your element psi of your Lie algebra and letting it act on the functional. So physically it means taking the gauge transformation with gauge parameter psi. So psi lives in S. Note this anti-symmetry here. If you want to now connect to more physical language, these psi's correspond to ghosts. So because we took anti-symmetric products, these are anti-commuting variables. These are odd variables. Okay, so the upshot is that if f is invariant, then gamma on f is identically 0, because any gauge transformation you take, any gauge parameter you plug into this, you will get 0 if f is really gauge invariant. So H0 characterizes the gauge invariant functionals. So you have two bits of homological tools, and now you want to combine them together to one thing. So this is the BV complex. Again, let me just throw in a bit of geometry. In fact, you can think of this complex here as the space of functions on a graded manifold. So this grading is important to keep track of things. So you can think of the elements of that complex as functions of your honest fields and of ghosts. So ghosts live in degree 1 and behave odd. Okay. So you can think of everything as functions on the extended configuration space. Okay, so this is how you obtain the BV complex. Now you combine two things. So you combine this extended configuration space where you have your original fields and the ghosts, and then you take a vector fields on that. So you combine what you did for the equations of motion with what you did for invariance. So this is then called the BV complex. So it has anti-fields because it has the vector field component. It has ghosts. It has anti-fields of ghosts. So it has a multitude of fields, but they are all they all play a role. They all have a meaning, and the thing you want, namely the space of gauge invariant on-shell functionals, is obtained in the end as taking the zero of cohomology of the BV differential. And this one is pretty simple in the two cases I want to focus on, so gravity and Young-Mills. It's just the sum of delta and gamma. Now, in general, this won't be true if you have theories with symmetries that don't close off-shell. Then there will be more terms here, but the point is that there are results saying that there always are only finitely many terms. So you always win in the end, even if you end up with very many fields. And again, using a bit of homological algebra, you find out that the way you set up these things, H0 of S would be H0 of gamma on H0 of delta. So just stepping back and unwinding all that algebra, this is exactly what you want. Okay, so that's exactly where this whole thing becomes useful. So you have the space you want, so gauge invariant functionals on the space of solutions, and you have a presentation of that in terms of some vector space with a differential. So now what you do is you quantize this vector space with that differential. And because I have limited time, let me just quickly sketch how to do it. Okay, so maybe I will skip that bit. So the quantization is not very different from what you would do in the scalar case. So in fact, okay, so you have some extended action, so you build that action in such a way that it's compatible with this differential. But this is also kind of outcome of your framework. So this BV framework produces the action, this extended algebra, and the differential. You split it into what might be the quadratic part and the rest, and you quantize now the quadratic part in the usual way. So in that BV setting, you can do gauge fixing. So you're in the situations where retarded and advanced green functions exist, and you can build the Pauli-Jordan function, which gives you the classical bracket. So this is the construction of pairs, and then you quantize this bracket using deformation quantization. Again, there are some technicalities which I don't want to go into, but this is standard. You don't worry about there being some extra fields. So this is an example. And then next you introduce time-ordered products. And again, this is a standard law of Epstein-Glaser. You introduce time-ordered products in such a way that they satisfy certain axioms, certain properties. But you will have extra axioms which ensure that things are gauge invariant in terms of that BV differential. Okay, so let me just maybe finish that. So the key player here is to define the time ordering operator using contracting with the Feynman propagator. This has to be made sense of using renormalization. So you can do it in the framework of Epstein-Glaser. And formally, this is the same as trying to integrate with the Gaussian measure given by the covariance given by this Feynman propagator. So this makes sense, and you define the time-ordered products, and okay, so let me skip that, and you define the formal S matrix as the time-ordered exponential. The interacting fields are then given by the formula of Bogoliubov, and they involve the perturbed formal S matrix and its inverse. This is again standard, doesn't differ much from the scalar theory situation. You can also introduce, in some cases, interacting star products, but this might not be well defined in all cases. But anyway, so you have these interacting fields, you have the S matrix, and you need some sort of compatibility with that whole BV BRST story. And here it comes. So a central equation in this framework is the quantum master equation, which essentially says that this formal S matrix has to be invariant under the linearized BV operator. And then, okay, for regular enough objects, you can rewrite it in the form which you might find in physics textbooks, or maybe, well, the work of Batalin-Wilkowinski as well. So this is, you see, this is a sort of condition for the time-ordered products, which you want to fulfill by using your renormalization freedom. Again, won't go into that. So this is the quantum master equation, and there is also the quantum BV operator, which is given by a twist of, again, the linearized BV operator with this map, which gives you the interacting fields. Okay, so this bit is crucial to recover the information about your physical observables after quantization. So you set up this whole BV story, then you perform the quantization in the usual way. You have the formula for the interacting fields, and in the end, you want to recover the physical observables as taking the cohomology of some operator, and instead of taking the classical one, you take the quantum BV operator, which is obtained by the deformation of the differential. Okay, I think, well, since I'm running out of time, let me just jump to the conclusion, because the rest is a bit of technical story. So yeah, I mean, what I wanted to convince you that the geometrical structures underlying BV fit very nicely into the PAQFT formalism, so can be used to quantize theories with local gauge symmetries. It's a way to do path integrals in Lorentzian, so you can think of it as translation of path integrals into more algebraic framework. For regular objects, these actually agree. So the quantum master equation agrees with what you would call the standard one. Okay, this I didn't have time to do, but it also works nicely in the renormalized theory. And the examples, at least I have looked at, were bosonic string and perturbative quantum gravity, and there is this nice paper of Stefan on Young-Mills theory. Okay, so that would be it. Thank you very much for your attention.
Other questions? Yes.
So there are advantages from your perspective to being directly in the Minkowski?
If you're working on curved space-time, then you don't always have the Vig rotation to your avail. So there, yeah, I would say there is advantage in working in Minkowski. And there are many things. So this perturbative framework of Epstein-Glaser, it works very nicely in position space in Minkowski. So there is a tool you can readily use.
So there is this approach by Kevin Costello, also using Batalin-Wilkowinski formalism. What are the main technical differences?
So the main difference is how the renormalization is done, because they work in Euclidean signature, so they use different techniques for renormalization. So I have a joint paper with William where we made comparison for the free scalar, for the scalar field without gauge symmetries. So these two frameworks can be related in the situations where both make sense. So if you can sort of Wick rotate, if you can make connection between the Euclidean and the Lorentzian situation, then they are equivalent. So algebraically, on the formal level, they are equivalent. But on the technical level, if it comes to renormalization, then Costello uses different methods for renormalization. But I think it should all come down to the same thing, at least in the situations where you can compare, because that, I mean, doing it on general Lorentzian manifold is a different story than doing it on general Riemannian. You cannot always connect. But they're very close together. So
I have a question. So with the quantum gravity, I always thought it was non-renormalizable. So if you define these time-ordered products the way you have, it's not a problem that this somehow corresponds to adding infinitely many counterterms.
But that's why I said it's effective theory. So if you stop it at certain energy scale, then it's, I mean, okay. If you try to relate it to experiments. So what we can apply it to, for example, is cosmology, and there you can look at cosmological perturbations as perturbations in quantum gravity, and then you can compute loop corrections to correlations of fields. But okay, I mean, there are no quantum gravity effects up to now, so we don't expect them to be terribly large. So that might work well in the regime where these effects are not very large.
Okay. There are no more questions.